When considering 350 kilowatts transformers connected together to create a three-phase service, the resulting service is not simply 150 kilowatts. The total power delivered depends on the configuration, voltage levels, and power factor of the load. To understand this, firstly, we must look at the power equations for single-phase and three-phase systems. For a single-phase transformer, the power, often expressed in kilovolt amperes or kVA, is related to the voltage and current by the equation kVA equals volts times amps divided by 1000. The power in kilowatts equals kVA times power factor, where the power factor is a measure of how effectively the electrical power is being used. A power factor of 1 indicates perfect efficiency, while values less than 1 indicate that some power is being wasted, typically due to reactive loads like motors and inductive components. Secondly, in a three-phase system, the power calculation is different. The total three-phase apparent power, S, in kVA is given by the equation S equals the square root of 3 times the line-to-line voltage times the line current, all divided by 1000. Similarly, the real power, P, in kilowatts is calculated as P equals the square root of 3 times the line-to-line voltage times the line current times the power factor, divided by 1000. It's essential to use line-to-line voltage for these calculations, which is the voltage between any two phases in the three-phase system. Thirdly, when transformers are ganged or paralleled, it's crucial to understand how they contribute to the overall service capacity. Paralleling transformers is done to increase the capacity and reliability of the system. Instead of having one large transformer, multiple smaller transformers share the load. This offers redundancy. If one transformer fails, the others can continue to operate, albeit at a reduced capacity. However, paralleling transformers requires careful consideration to ensure proper operation and prevent circulating current. The transformers must have firstly the same voltage ratio. The turns ratio, which dictates the voltage transformation, must be identical. Even slight differences can lead to circulating currents, reducing efficiency and potentially damaging the transformers. Secondly, the same percentage impedance. The impedance of each transformer should be the same percentage of its kVA rating. This ensures that the load is shared proportionally among the transformers. Differences in impedance can cause some transformers to carry a disproportionate share of the load, leading to overheating and potential failure. Thirdly, the same phase shift. In three-phase systems, the phase shift between the primary and secondary windings must be the same for all transformers. This is especially critical in delta Y or Y delta configurations. Incorrect phase shifts can cause severe imbalances and potentially damage the system. Fourthly, similar kVA ratings. While not strictly required, it's generally best practice to use transformers with similar kVA ratings. This helps ensure that the load is distributed evenly and that no single transformer is overloaded. Considering a scenario involving 350 kilowatts transformers, each transformer provides 50 kilowatts of power at its rated voltage and current. However, the overall three-phase service capacity depends on how these transformers are connected, which can be either delta-delta, Y-Y, delta-Y, or Y-delta configuration, and the voltage levels involved. The total apparent power, S, delivered by the three transformers is indeed the sum of their individual kVA ratings. If each transformer is rated at 50 kVA, then the total apparent power would be 150 kVA. However, the real power in kilowatts that can be delivered to the load depends on the power factor of the load. If the load has a power factor of 1, then the real power would also be 150 kilowatts. But if the power factor is less than 1, the real power will be less than 150 kilowatts. For example, with a power factor of 0.8, the real power would be 150 kVA times 0.8, which equals 120 kilowatts. Therefore, with a power factor of 0.8, the system could only supply 120 kilowatts of real power. Furthermore, it's essential to consider the transformer connections. In a delta-delta connection, the line voltage is the same as the transformer voltage, and the line current is the vector sum of the transformer currents. In a Y-Y connection, the line voltage is the square root of 3 times the transformer voltage, and the line current is the same as the transformer current. In a delta-Y connection, the voltage and current relationships are more complex due to the phase shift introduced by the transformer connections. Therefore, the specific configuration affects the voltage and current relationships and the overall service capacity. Moreover, the nameplate rating of a transformer indicates its maximum output under specific conditions. The nameplate typically includes the kVA rating, voltage ratings, frequency, impedance, and temperature rise. The kVA rating specifies the maximum apparent power the transformer can deliver without exceeding its temperature limits. Exceeding these limits can damage the insulation and reduce the transformer's lifespan. The voltage ratings indicate the primary and secondary voltages for which the transformer is designed. Operating the transformer at voltages outside these ratings can cause insulation stress and potential failure. The frequency rating indicates the frequency of the alternating current for which the transformer is designed. Operating the transformer at a different frequency can affect its performance and efficiency. The impedance of the transformer is expressed as a percentage of its kVA rating and indicates the transformer's ability to withstand short-circuit currents. A lower impedance transformer will allow higher short-circuit currents to flow, which can be damaging to connected equipment. The temperature rise indicates the maximum temperature increase the transformer windings can withstand above the ambient temperature. Exceeding this temperature rise can degrade the insulation and reduce the transformer's lifespan. In summary, while 350 kW transformers might suggest a total service capacity of 150 kW, the actual power delivered depends on several factors. Firstly, the load power factor. Secondly, the transformer connection configuration. Thirdly, adherence to the transformer nameplate ratings. Careful consideration of these factors ensures that the transformers operate within their design limits and that the electrical service meets the demands of the connected load without any issues or failures. Always perform detailed calculations taking into account these variables to accurately determine the capacity of a three-phase service made up of GaN transformers. Therefore, it is not simply 50 kilowatts times 3 equals 150 kilowatts.